calculate K, the equilibrium constant for the above reaction. Okay, so let's write the reaction again. We have Cr2O7 minus plus 14H plus 3Zn going to 2Cr3 plus 3Zn 2 plus, and is 7H2O, right? And the standard cell potential for this is equal to 2.09 volts. So 2.09, not 2.11. 2.11 was the cell potential under non-standard conditions, whatever we happen to, the different concentrations. We're using standard. So we said that the standard cell potential is equal to RT over NF ln K. So we get ln K, sorry I flipped them around, NF E standard cell divided by RT. Okay, that's equal to 6 moles were transferred. 96,485 coulombs per mole, 2.09 joules per coulomb over 8.3145 times 298 Kelvin. We get K is equal to E raised to the power of this thing, which is equal to 488. 488. I'm not even going to write this number down. I'm just going to leave it as e to the 488. Huge. This equilibrium constant is huge. You know what that means? A huge equilibrium constant? That means the reaction is so far to the right. That means once this reaction is done, there is virtually none of this left. Everything has turned to chromium 3+, everything has turned to 7 zinc+, and there's a whole bunch of water floating around in that cell. Now at equilibrium, yes, there's always a little bit of reactant left, but in this case, you know, this is so huge that it's not even noticeable. That equilibrium is actually a theoretical state. This is definitely completion at its best. This is very typical. Large K values, large equilibrium constants are very, very common for oxidation reduction reactions. Very common for redox reactions. When you take a piece of wood and you burn it, is there any wood left at the end? No. That's an oxidation reduction reaction. You're taking organic matter and you're converting it. You're oxidizing the carbon. You're turning it into carbon dioxide and water. When you ingest the food that you ingest and your body converts it to glucose so that it can oxidize that glucose aerobically under oxygen conditions, and it converts it to carbon dioxide and water, it's an oxidation reduction reaction. The carbon in the glucose is being oxidized to, well, it's being oxidized to carbon dioxide. So the fact that these things release so much energy is confirmed by the fact that the equilibrium constant is going to be very, very huge. You're not going to have a lot of reactant left over. It's going to be all product. That's the whole idea. So again, we have all of these wonderful, wonderful equations that we've been working with. We have the thermodynamic versions of those equations. We have the electrochemical version of these equations, and they're all just expressing a relationship between these things. Free energy, cell potential, equilibrium. All of these things are tying together. Remember when we started back discussing equilibrium? We moved from equilibrium, we moved to thermodynamics, and now we closed off with electrochemistry. So we only have one more thing to discuss regarding electrochemistry. The next time we're going to talk about something called an electrolytic cell. We've been talking about a galvanic cell, which is a spontaneous process. Well, what if I don't want to do the spontaneous? What if I want to push energy into the system and make the electrons go in the direction opposite to where they want to go normally. If they want to flow this way, I want to push them back the other way and run the other reaction. Well, that's when we're going to, that's called an electrolytic cell. Very, very important process industrially and for all other things. It's how you recharge your batteries. When a battery discharges, we push the electrons back through the wire and back into the original compartment they came from, like a NiCad battery. We recharge the battery, and now the battery's ready to go again. So until then, thank you for joining us, and we will see you next time on Educator.com. Bye-bye.